I can go ahead.
No, go ahead and share it.
All right,
Thank you.
thank you. All right. Good afternoon,
It would
everyone.
be nice. It would be nice to have a Mozambican introduce a Mozambican.
Uh, all right. So, good afternoon, everyone. It's my pleasure to introduce today's speakers, Mrs. Yara Simango. So, Yara is a PhD candidate pursuing a joint doctoral degree between the University of Bristol and the University of Cape Town. Her research focuses on the mass modeling of galaxies, investigating how their mass distribution has evolved over more than a billion years of cosmic time. So behind her research, Yara is deeply committed to astronomy education and public engagement. She's active member of Mozambican Astronomical Society, where she leads and supports educational and outreach activities aimed at promoting astronomy within Mozambican community. Yara is also a former Dara scholar, having completed her master's degree at the University of Leeds through the Dara Advanced Scholarship Program, which support the development of astronomy and space science across Africa. Today, she will share her research with us, and we are delighted to have you, Yara. Please join me in giving a warm welcome to Yara Simango, and thank you, Yara, for joining us today. The floor is yours.
Thank you, Francisco. Hi, everyone. As he said, my name is Yara Simango, and I'm a PhD student at University of Cape Town and University of Bristol. Thank you, Professor James and Francisco and Willis, for inviting me for this seminar here. I will try to explain what I am doing for my PhD. I forgot to ask how long was the seminar. So first I had prepared a shorter seminar, but then I think I will take longer explaining the scientific context of my research, which I didn't plan to, so I don't have plenty of slides on that. But then since time allows me, I will try to do that with the slides that I have. So the title of my research is Mass Modeling of Galaxies over a billion years of cosmic time. I will try, I will start by the scientific context of this research. So first of all, mass modeling is the decomposition of a galaxy's rotation curve into the contributions from its individuals dynamic components. I mean, gas, stars, and dark matter. This is very important because knowing the contribution from each of the individual components of the galaxy provides insights into the distribution of these components in the galaxy, and also it provides uh, important insights into the properties of dark matter halos, which are structures that we cannot see. They do not interact with us via electromagnetic waves. So, one of the ways of knowing the properties of this matter is by decomposing the galaxy. So, to do that, we normally use neutral hydrogen observations from interferometric data, because interferometric data provide good resolution that can trace uh, hydrogen gas beyond what the optical shows, where the rotation curve is mostly dominated by dark matter. So if we have rotation curves measured in different cosmic epochs, then we can have inputs to test galaxy evolution models. However, what happens is that today's studies of galaxies and galaxy kinematics, they only rely at high redshift, they only rely in optical and molecular gas tracers, which has the limitation of not extending to high radii because of uh, the diffusion of the H1 gas. So in high redshift, our instrumentation cannot detect H1 gas. So if we can study the rotation curves at different cosmic epochs using radio data, we could have a lot of information about dark matter and galaxy evolution. So I've already mentioned here the motivation, right, of this work, but then I will explain it a little bit more. The recovery of rotation curves are strongly affected by observational limitation. If we don't have good resolution, good sensitivity, and when I say resolution, mostly the spatial resolution, but also spectral resolution, then the reliability of the recovered rotation curve is affected, which will affect the galaxy mass model. So understanding the biases that are introduced by poor resolution into the recovery of the rotation curves will make us study more accurately rotation curves recovered from galaxies that are located at higher redshifts than our local universe. And to do that, we want to quantify the systematic effects that are introduced by poor rotation curves, poorly resolved systems. Sorry. Yeah, so this project aims to quantify the systematic effects that are introduced by poorly resolved systems. And how are we going to do that? By picking observations of local galaxies that are well resolved and model these galaxies, and then modify these observations and make them look like they were observed at higher redshifts, look like they had poor observing conditions, and then compare the rotation curves and the results of mass modeling to see if we have patterns that we can now develop a correction factor for galaxies that will be observed far away from us by future H1 surveys, and that will be done using the Meerkat and the future SKAO MID. And to do that, we started with one particular galaxy called NGC 45. So for this galaxy, this is a nearby galaxy, is located at 6.6 megaparsecs. We derived the optical properties, the radio properties of the galaxy, modeled the kinematic of this galaxy, and then performed mass modeling. Then degraded the data of this galaxy to where the galaxy is only resolved by 3 beams elements across the entire galactic disk. So we did that because this is the actual limitation of the kinematic modeling softwares. So before I proceed to all the methodology that was used for this galaxy, we started using data from the Imagine survey, which was observed using the Australia Telescope Compact Array. So this data wasn't collected for the purpose of the research that I am doing. The Imagine survey has no published paper yet, but the observations were carried out to understand accretion mechanisms into galaxies. So the survey itself was more focused in having good sensitivity to be able to detect diffuse gas and try to understand accretion and outflows of gas in galaxies. They observed 28 galaxies. However, the data was sitting there in the archive, and my supervisors were part of this survey, and the data is also useful to do mass modeling. And then we picked this data to do mass modeling of this galaxy, because this is a galaxy that has a simple structure, as you can see here from this optical image that I'm showing here. It's a galaxy that has no prominent bulge, and it has a disk. It's located nearby, so the structure is simple to decompose into the dynamical components. The resolution isn't that great as studies of mass modeling are, but this was the pilot study to understand how mass modeling is done, how is the procedure of data reduction of a spectral line interferometric data. So here is the global H1 profile that was derived from the data. Here is the data cube after the data reduction that I performed using a software that is specific for data taken by the ATCA, which is Myriad. So I got this data cube here for the galaxy, and then derived the H1, the global H1 profile, used it to measure the integrated flux, the total H1 mass, the extension. I produced the moment zero map to measure the extension of the H1 disk, the peak H1 column density, systemic velocity, and other radio properties. And here is the velocity field of the galaxy, showing an standard structure for spiral galaxies. And after that, the data cube was introduced to a software called 3D Barolo. This software does a kinematic modeling using the tilted ring model, where it fits concentric rings to the three-dimensional data and then produces kinematic information. Here I'm showing the rotation curve of the galaxy and the velocity dispersion of this galaxy. So the main ingredient that is used to do mass modeling of galaxies is this rotation curve, because this is the speed of the galaxy due to all the components of the galaxies, including what we cannot see, which is the dark matter. So if we decompose this, we can use the radio information that we have to have the gas component, we can use optical or infrared information to have the stellar component, and then the remaining rotation curve is due to the dark matter halo. And then, so we still using the radio data. One of the outputs of 3D Barolo is the surface mass density profile that will quantify the mass and the velocity profile of the gas in the galaxy. We do correct the gas for helium as well. And then we also used infrared data from the Spitzer IRAC 1, which is taken at 3.6 microns, to have the surface brightness profile of this galaxy. As you can see, the optical information doesn't reach to this radius that this radii that we achieve with radio. We only have the inner disk, and the optical image also that I showed in previous slides. You could see that I overlaid contours from the radio, and the optical part is only at the center part of the galaxy. So because of the model that we used for mass model, the software used, it does not need to take the data to do the mass modeling. We need to fit functions to this data to give as input for software called Galpynamics, which decomposes the rotation curve. So the function to model the surface mass density profile is given by this equation, and it is this orange line here and the function to model the stellar surface brightness profile is given by this red dashed line here, and it's a Cerseic function within n equals to 1, which is an exponential function. So this surface mass density, this surface brightness profile is then converted into luminosity, and then from the luminosity it is converted to mass using a constant mass to light ratio of 0.5. Later on, I will show together with the degraded cubes what is the output of the mass modeling. So, because the main goal is to know what poor resolution, sensitivity, and ultimately also in the next projects, we will also add spectral resolution. So I created the set of data cubes from the original data cube that we had. As you can see, the resolution isn't that great. So the original data has this resolution that you see here, which gives us 5 beams across the galactic disk. And then it has this signal to noise. And then I spatially degraded this data by convolving the data cube to a circular beam with these characteristics, and this gave us 3 beams across the galactic disk. This table had to be updated because when we smooth spatially the data, we end up gaining more sensitivity. So the sensitivity, we start picking up things that are mixed with noise. So we got more sensitivity for this cube, around 80, signal to noise of 80. And then I added noise to the original data just to simulate conditions of poor signal to noise, maintaining the resolution of the data. And then in the end, I combined these two, adding noise and convolving the galaxy to see what effects would come from that. Yes. So what we saw here is that spatial resolution is the main is the main is the main observational effect that affects the kinematic modeling of a galaxy and consequently the mass modeling of a galaxy, because it introduces beam smearing, which flattens the inner parts of a rotation curve, broadening the recovered velocity dispersion as well at the same time. And it also redistributes the gas surface density, producing less centrally concentrated H1 disk, which will have effects on the mass modeling as well. While sensitivity degradation has little impact on the rotation curve and significantly suppresses the velocity dispersion. This suppression of the velocity dispersion ends up enhancing a little bit the rotation curve. If we are dealing with dwarf galaxies, in this case, it's not the case of my research, the suppression of the dispersion velocity would imply in corrections of in pressure support corrections, because the difference between the dispersion and the rotation velocity would reduce. So the combination of both the spatial resolution and the signal to noise does not linearly propagate, like it doesn't add up linearly the biases that are introduced in kinematic modeling and consequently in mass modeling, but it introduces distortions in the modeling, particularly in the inner regions of the galaxy. The ability of the software to model the galaxy degrades a lot, both for kinematic and mass modeling. So here I'm showing the outputs for the original data and the degraded data. So we have 3 main outputs from the kinematic modeling. We have the rotational velocity or rotation curve, then we have the dispersion velocity, then we have the surface mass density profile, which is what brings the contribution from the gas in the rotation velocity of the galaxies, this plot here. So for the axis of the first is rotation velocity as a function of radius, and the orange dots are of the original data, and the red dots are of the spatially degraded on top, then signal to noise degraded on the middle, and then both degradation on the bottom. As you can see here, we barely have accurate information of the inner parts of the galaxy, and this is something that introduces problems to an already existing problem, which is called the cusp core discrepancy, where um, we don't know if the galaxy rotation curves of some galaxies, they rise steeply as predicted by models, or slowly as observations tend to show. So for the dispersion velocity, you see here in the first plot, for the spatially degraded cube, the dispersion velocity is enhanced, but then here in the signal to noise degraded cube, it is reduced. And when both degradations happen, the spatial resolution is what affects the most. We see the dispersion velocity not so low as in the middle. As for the surface brightness profile, for the sensitivity case, basically the surface density profile is not affected. While when spatial resolution is introduced, it is lowered, especially in the inner part, where I said we have less concentrated H1 disks. And here is what the consequences of what happens with the kinematic models are propagated into the mass modeling, or because the mass modeling doesn't happen without the kinematic modeling. We pick the outputs from the kinematic modeling and then we do the mass modeling. So the spatial resolution degradation will produce a systematic effects, the largest one, which favors a less concentrated and more extended halo solution. So for the dark matter, which is what we are trying to measure some physical properties, we see that when the galaxy is not very well resolved, we will think that the halo is less concentrated and is more extended than it is. And for the sensitivity, the precision of the recovered halo parameters is affected. So the RMS noise of the I forgot the term that is used, but when we do the reduced chi-square for the modeling, it is poor when sensitivity is degraded, and then when both are combined, it weakens the ability of the data of the model to constrain dark matter halo properties. So here is the model where we compare what happens with original data cube and then with degraded data cube. So the continuous line is the well into, well resolved data, because it's not very well resolved as I've shown you. But for the well resolved data, we have these dots here, which are the rotation curve, very well resolved, and the model is the purple continuous line. So the model kind of follows the data, but then when the cube is not very well resolved, the total rotation curve from the model is slightly lower in the inner part and a bit enhanced in the outer part of the rotation curve. And we see that this model, this is the NFW model. The dark matter parameter is showing a different behavior in the inner part if we compare with the dark matter rotational velocity of a data that is well resolved. And this also happens with the gas contribution. So the stars, they don't change because we didn't change the stellar data. The reason why we didn't change is because we do have good quality data, infrared and optical data at the red shifts of 0.5 of 1, which is not the case for radio data. And as you can see here, when we degrade spatially our cube, we gain some sensitivity. So we can pick up emission that is mixed with noise. So here we were comparing the sensitivity case, which is less affected, and the combination of the two, which is the most affected model. So moving forward, after finishing the work of this NGC45 Galaxy that is in the way to be published, we know that results of only one galaxy are not really meaningful to have statistical conclusions. So we need to get a bigger sample and with different types, not morphologically, but with different types of galaxies in terms of adding more complexity to that one morphology. We are working uh, with spiral galaxies, but in the spiral galaxies we have spirals with a bar, without a bar, with a prominent bulge and without a prominent bulge. And the way observational limitations will affect these different type of galaxies is different. For example, if we have a galaxy with a prominent bulge that is located in the nearby universe, in the local universe, we will be able to have information of the bulge and information of the disk. But if we move further to higher redshifts, some results from the JWST have shown that some galaxies were misclassified morphologically by Hubble Space Telescope because of the ability to detect blue light. So some aspects of the inner part of galaxies in this wavelength were not detected, and people were classifying spirals as elliptical galaxies. So if we are doing surveys using the SKA and MeerKAT at high redshifts, we may get into galaxies at higher redshifts that we think they are different from the galaxies that we observe locally, while that's not the case. In fact, it's the ability of detecting the light that is coming from these galaxies that is limited from our point of view. So here we won't only degrade the radio data, but also, if needed, the infrared and optical data that will be used using K corrections. It's something I'm still investigating. I don't know because I've not done it yet. But so for the bigger sample, we are using the Spark database has a parent sample to do this big sample mass modeling and degrade this data, also do the modeling and compare to see if we see a pattern in our results. So we're using this database because it has uniform infrared data for it. And we also have very, very high resolution radio data from different surveys, not from one. So we apply some selection criteria in this parent sample. We only pick galaxies within this range of inclination because face-on and edge-on galaxies are very complicated to model. So we excluded these galaxies for now. And in terms of morphology, we also pick galaxies that are rotationally supported. They have rotationally supported disks. So we exclude blue compact dwarf galaxies. We are not working with dwarf galaxies in general. We are assuming that if we are doing surveys at high redshift, we won't be able to detect dwarf galaxies anyway, for now, even with the capabilities of the SKAO. So after applying the inclination and morphological criteria from the original 175 sources from the Spark database, we remain with 90 galaxies. And these 90 galaxies then were cross-matched with available H1 surveys because we want to have data, radio data, that we are not going to reduce the data like we did for NGC 45 because of time. Instead, we will pick data cubes from other surveys. So some of the galaxies that are used in the Spark paper, they are from individual researches and they are not available, or some of them they are very from old studies. We cannot get the data. So we cross-matched with things, halo gas and WISP, and we found out that we can get these galaxies, 34 for WISP, 9 for halo gas, and 9 from things. And then I downloaded these galaxies and I'm working with these galaxies now. And 38 of these galaxies have no H1 cubes available in the literature. So now with these galaxies, we have to measure the angular size of the galaxy. This is an example of one galaxy, how the angular size was measured. So I defined the threshold for what we call emission, that is 1 solar mass per parsec square, and then use the convex hull, which is a geometric package from Python, to have a polygon that surrounds the emission from the galaxy, and then measure the highest line that connects 2 points, and then that is my angular size. It's very important because with the angular size, I will use the small angle geometry to determine the intrinsic size of the galaxy, which doesn't change regardless. It doesn't change. Even if we are at higher redshift, the intrinsic size of the galaxy is the intrinsic size of the galaxy, while the angular size will now change because it's the apparent size of the galaxy. So here we have one example of the measurement of the angular size, and then we get the intrinsic size using this equation. And then now we start targeting a set of redshifts. This set of redshifts is for us to degrade our cubes to this redshift. And these redshifts were not randomly chosen. They were chosen based on the H1 surveys, the current and the future H1 surveys. So the Laduma survey, done using Meerkat, is going to observe resolved galaxies up to 1.4, a redshift of 1.4, using the UHF band. So that's why we are going to mock observations at those redshifts. And then because as the redshift changes, the angular size changes, the beam size of the observing telescope changes. So we need to estimate using the intrinsic size, physical size of these galaxies, what will be the angular size for each of the redshifts. And then this is helping because we cannot, in fact, if we have a cube that was observed using the halo gas, I cannot mimic a meerkat observation because the beam from the meerkat is smaller than the beam from halo gas. What I can do is the equivalent number of beams across the galactic disk that would be obtained using the meerkat. So I will get the number of beams across the apparent size of the galaxy using the meerkat at that redshift, and then degrade my cube to have the same number of beams. And then that's how I'm mocking a meerkat observation in my own object. So even though I am aiming to all these redshifts, they won't be possible to all galaxies because we will have what we call a useful redshifts, where I estimate the number of beams, meerkat beams, in such systems. And if the number of meerkat beams is higher than the beams that we already have, we cannot do anything about that. And if it's going to be smaller than 3, it's also not worth it doing, because the softwares for modeling the kinematic of galaxies, they work, we can trust them up to 3 beams across the galactic disk. So then, because of that, we have the number of useful redshifts for each of the galaxies. So for now, I only worked with halo gas galaxies. I'm already working with things galaxies, but I didn't bring to this talk. So as you can see, I have plenty of redshifts here, but for the 7 halo gas galaxies I'm working with, I can only keep up to this redshift of 0.085, because after that I have less than 3 beams across. Yeah, and then I will also have to mock the spectral resolution, because as we move to different redshifts, the velocity width doesn't remain the same for the same frequency width. So we have to estimate what will the velocity width of such observation at this redshift using MeerKAT would be, and then smooth our velocity width of our data cube, and then get a different velocity width, and for sensitivity as well, using this equation here. We will, because as we observe galaxies at higher redshifts, the flux density reduces, the galaxy becomes fainter. But we cannot make a cube fainter. We cannot dim the flux of our actual cube. We are mocking an observation. So we will get the equivalent signal to noise ratio, and what is possible to do is adding noise to the cube to achieve the same signal to noise ratio that we would have with a galaxy that is far away. Not just dimming the flux, but also some MeerKAT papers from in the literature, we see the sensitivity variation across frequency bands. So since the observing frequency of the H1 line changes with redshift, operating in different bands will mean different RMS noise. So that RMS noise will also come into the sensitivity scaling of my mocked cube. And then once we know all the parameters that we are aiming for, it's just picking the cubes and degrade them, which I'm doing now. I'm currently modeling all the data cubes that I have. Now I have 34 data cubes. I'm doing the kinematic modeling of these data cubes, because the rotation curves are already available in the literature. I am comparing my rotation curves just to see how accurate I'm doing the work, and then I will degrade my data to the parameters that I have estimated and do the work again. Why am I not picking the rotation curves that are already available? Because the work has to be consistent. The same way I'm deriving the rotation curves for the local original data cubes should be the same way I will do it for the degraded cube. So I have to do all the work so that I can see the biases that will be introduced. So I have to model, compare with what the literature has, and then model degraded cubes, and then measure the parameters that will allow us to compare things like inner slope of the rotation curves, things like flat velocity, which is mostly used for scaling relations, and then see how degraded the cubes appear to be. And in future works, we can see if observations from high redshift galaxies could be corrected so that we can have more accurate information about individual components of the galaxies and parameters of dark matter halos. And that's all. Thank you. I hope I know I did not exceed the time.
Oh, thank you very much, Yara. That was very, very interesting. Yeah, I'm really impressed. Um, Yeah, so I would like to open the floor for questions. And if you have any question, please unmute yourself and ask. Yes, Prof. Catherine.
Hi, thanks for the nice talk. I was just wondering, I mean, it's for one, it's very nice to see that the effect of the beam smearing on rotation curve measurements is now very much better understood. I mean, it was historically quite a point of contention between people who did these kinds of observations, because they said that the distribution of dark matter was not consistent with CDM, cold dark matter, not consistent with standard models. So it's nice that this beam smearing effect is being understood better. But just kind of connected to that, in hierarchical structure formation, we expect that there are small clumps of dark matter in the halos of galaxies. That's kind of what we assume, what the model expects. And so then I wonder about this Barolo tilted ring modeling. I mean, does it really take into account perhaps the non-axisymmetric and perhaps not very homogeneous halo, given that we expect some of these clumps? Thanks.
Yes, thank you, Professor, for the question. Yes, Barolo is actually very good. If you're dealing with a complex galaxy that you would expect these clumps of dark halo, dark matter, you can, in the parameter file for the model, you can let the model fit uh, different parameters. So you choose what you are interested in fitting, and you can let it fit things like radial velocity and other parameters that for simple structured galaxies, they are not really useful. And from what I've been reading, Barolo is quite good. It's not perfect, obviously. And now I will be dealing with complex galaxy structures that I've not done it yet, because the first galaxy I worked with was very simple. So I couldn't have these complexities in my work that I will be adding now, modeling galaxies more complex than what I had.
Okay, thanks.
Yes, Raul, can go ahead.
Hi, very wonderful talk. I have a general question. I just want to know how does a broad velocity dispersion affect the kinematic modeling?
Okay, sure. Normally for massive galaxies with a rotation velocity above 100 kilometers per second, the velocity dispersion doesn't affect much, because the difference between the dispersion and the rotation is very big. But then when we are dealing with dwarf galaxies, the dispersion velocity plays a role in the pressure support for the galaxy. So we need to balance the gravitational support. How can I say, the gravitational bound of the galaxy, what keeps the structure rotating with the same velocity, will be affected by the dispersion of the components of the galaxies. So we need to correct for that. And the current kinematic modelings, they do have the option to do correction for pressure support that is introduced by dispersion velocity in this type of systems. I didn't need to apply the pressure support correction, because the difference between the rotation and dispersion velocity for the galaxy I worked with is 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 around 80 kilometers per second. So it's almost negligible, the effect that the dispersion velocity will have. And I'm not going to be dealing with dwarf systems, so I will probably not need to do this correction.
Thanks, Raul, for the
Thank you
question.
so much.
Yes, Prof.
Thanks, Yara, for the nice presentation. I have two questions. One is on the first set of modeled rotation curve you had. One of the plot had very huge errors in the data points. And yeah, so with such very big errors, how are you able to constrain these parameters? Well, how were these errors derived? Why are they so large?
Yes. Well, I forgot how to explain exactly what Barolo does for for computing the errors, but it's not a robust way of constructing the errors. It's the previous versions of this kinematic model couldn't even compute the errors, and the errors are very high, especially at the outer parts
Mm.
of
Are they statistical errors? Or
I think so.
okay.
Yes. But I can't explain what the model does. But one thing I remember is that even the documentation explains that it's not a very robust error construction, I would say.
Okay. Maybe my next point is on the beam smearing, because I didn't get it quite well when you mentioned that if you have two beams over a galaxy, then the software fails. And if you have something like a three beam system over the galactic disk, this is the assumption that the central beam is pointing around the center of the galaxy, and then the other ones are on the sides. This sounds a bit counterintuitive, because it's still a function of how the beam is placed and how much overlap between the beams. Can you explain that part a bit more?
Yes. Yes. So what Barolo does when it is modeling the kinematic of the galaxy, it places each of the rings in the center of the beam major size. If I let Barolo model and do the separation of each of these rings by default, it will choose the separation of the rings that is the size of the beam major of my observations. So starting with the center of the first beam, and it does this for one side of the galaxy. So if in my galaxy I only have three beams elements, it means that I will only have one approximately, I could stretch to two data points to characterize my circular velocity. And if the beam is too big, like in my second case, for example, we will have points that have the same velocity, because in that ring, the velocity was averaged to the beam, and I want to have the actual information of the velocity change along the radius when I'm doing the model. So Barolo cannot do the model. It needs to have at least three beams. That's the minimum it can run the model. And the more beams, the more resolved the galactic disk is, I will have more beam elements where it can distinguish the kinematic information of the galaxy. I don't know if I explained it properly, but I think that's the case.
Okay. What happens if you make the beam smaller and then have 5 or 6 beams spread across the entire galaxy?
If the What happens if I make the beam
If you
smaller
make
or
the beam smaller,
separate?
yeah. In the beam smoothing, so essentially you're making it larger, right?
Yes.
Yeah. So if you don't make it too large, let's say you take an intermediate size beam,
Yes.
and then you have, instead of 3, 4, or 6, which you
Yes.
place across the entire galaxy, what does Barolo do?
Well, for this specific galaxy, I only had 5 beams in my original data cube. So I could reduce to 4 beams. And
Yeah.
when I have the 4 beams, I have something like, if I'm spacing by the whole beam major axis, I have around 3 beams in each side. So I have more kinematic information, or I can have different velocity information because they were not averaged within the same radius. And
Okay.
then as I increased the beam, I put all the rings almost having the same information, and more beams I can, if the velocity is different, distinguish the different velocity values. So now that I'm working with galaxies that have like hundreds of beams across the galactic disk, I'm actually having the problem of oversampling. Because Barolo by default works with a one major axis, has the separation. Literature says I could even do half, it's still fine, which is what I'm doing here, half of the beam, because I have like 191 arc seconds of the beam major. So I'm placing the rings at half of the beam. But then now I'm dealing with situations where I have to double the beam to make one ring separation, because I'm having plenty of rings where no much information is changing. So there is no need to have all these rings transmitting the same information. So I'm just increasing the ring separation because the information is basically the same. But when it's the opposite, I'm having less rings where the information is changing a lot. For example, if in these 3 points, maybe if I had more sampling, I would see this variation not being so the English word is, but so brutal. Like, I would see the gradual change of the velocity in between these rings, probably.
Okay, thank you.
Prof. Chris, your hand was up. I don't know whether it was by mistake or you wanted to add something.
It's just a comment on the error bars in these plots. I think it's a sign that, and you can see it almost, that these points are not linearly independent. They're sampling some of the same data, and so that's why those error bars, don't they show signs of lack of independence. Yeah.
Which
Yeah.
is true. Which is true. Yes. Thank you, Prof, because this is very important for me as well. Because I see where I'm doing now with independent rings that they don't belong to the same beam. I'm seeing smaller errors than those ones here, where I'm placing 2 rings at the size of 1 beam.
Cool.
Okay, thanks for the comment, Prof. Chris. Eliab, I don't know whether you also had a comment or your question was clarified throughout this explanation.
Yes, thank you. It was clarified.
Okay, thank you. Any other question for Yara Simango before we close the section? Yeah, but maybe I can throw one question, maybe the last one. I'm just curious about the broadness that you showed on the spectral line, H1 line. I think it's the slide number 5. Yeah, this one. I'm just curious about this double peak. What does it mean exactly? Because in terms of galactic science, when you get double peaks, it tells you something. But then I'm not sure whether in galaxies the same interpretation is applied. And also, how did you get the systematic velocity of the source? Did you estimate from your line, or you used literature based from
I
the literature?
estimate, well, I estimated, I used intensity weighted and then midpoint systemic velocity, but I compared with the literature, and the values are similar. About the profile, I don't know. I don't know. The interpretation of double peaked.
But this
Yes.
is typical H1 profile, right?
Yes,
It's
this is
not-
typical for our H1 profiles, or the majority of H1 profiles that I've seen, they are double peaked. Yes, I never stopped to check why are they double peaked.
But then is it double peak?
Sorry,
Is it double peak with
that's
the
kind of
same
the
intensity?
central idea for its rotation, right? That's, you see a double peak when there's
Oh
a
yes.
yes. So the one side of the galaxy is coming towards you, blue shifted, the other side's going away, it's red shifted. I guess you might ask, why is there less emission in the middle?
Middle, yeah.
So, and yeah, I think that's, if you think about where all the H1 is in a galaxy, that also makes sense. But yeah, so it's just the double peak, just rotation, and one side coming towards you, one side going away.
Well, the absorption in the middle is mostly because that corresponds to the systemic velocity of the source of the galaxy itself. So you expect that some of the emissions around that center, typically that spectrum should be Gaussian in shape. Every physical line emission must show Gaussian distribution if it has to obey the laws of physics. But around the center, if you have anything, Francisco, you may have seen it from your own galactic observation. If you look at CO emission, for example, around the systemic velocity of the source, most of the line, you'll see absorption effect, which is just a continuum line absorbing things, or what you call self as absorption. I think that's what's happening here.
Okay, thanks for clarifying, bro.
Yeah.
Sorry, you think that the H1 is being absorbed in the middle?
Yeah, around the systemic velocity, I think that's absorption effect likely.
The assumption is that where galaxies are optically thin in H1, I think. So I think there's probably, if you just think about the distribution of gases at different velocities, there is not so much emission at that velocity, but I don't think it's absorption. I mean, yeah, the generals, the standard law is that galaxies are optically thin to H1.
Okay, maybe we can check it and reconfirm which one it is. There is also another aspect you can have a look at that I thought about when I saw your illustration. Did you check with the rotation if you're seeing something Keplerian as you go to the inner part of the disk?
I did ask my software to fit. First, I did not fit radial velocity. I think radial velocity is what would help me. I don't know if I'm wrong, but I didn't model that at first, and then I decided to do so because when I was checking the PV diagrams for my model, the model was struggling to fit some emissions that I thought maybe would be due to some Keplerian motion, but the radial velocity is too small, very small, in orders of tens. Yeah, so I don't think it is in this galaxy.
Okay.
All right. Any other
So
question?
I quickly checked this now, and the information I got is typically due to the kinematic effect. But if you have a case where there is edge-on view, then absorption, self-absorption can kick in. So you just have to check the inclination. And I think the source you showed now typically is edge-on, because face-on views you have very narrow velocity width.
Thank
I think
you.
she said that they deliberately didn't do the edge-on ones.
Sorry?
I think she said they deliberately they didn't do the straight edge-on. They do
Yes.
somewhere between edge-on and face-on, because then it becomes easier to model. Yeah.
Yes.
Yeah.
Say between edge-on and face-on, if you have a face-on case of a galaxy, how do you see the velocity structure?
You don't. That's why they don't do the
Yes,
face-on.
you don't see it.
Yeah. So this is edge-on, right?
No.
It's between edge-on and face-on.
This one has
Not edge-on?
this one has an intermediate inclination. It's around 50 to 52 degrees.
That's almost edge-on, right?
It's intermediate because we start seeing, well, it depends, because I've seen some papers calling a galaxy at 60 degrees an age on galaxy. But then normally, well, for me, I excluded from 75 degrees and started considering age on systems.
Okay, good.
Rahul, yeah, we're running out of time, but maybe this will be the last question. Rahul, you can go ahead.
Thank you, Francisco. I'm just curious to know, why are the extended galaxies difficult to model?
Extended.
Yes, so why is the extended difficult to model?
I don't think they are difficult to model. Actually, dwarf galaxies are more difficult to model than extended galaxy. You mean a large galaxy with more diffuse gas that can be detected when you say extended galaxies?
Yes.
I don't think they are difficult to model unless their inclination is high or very small. But other than that, if they have complex structures, then yes. For example, if they have a prominent bulge and a bar, they will be difficult to model, because when we are coming to the stellar component of the galaxy, only one exponential function won't be enough to describe the surface brightness profile of that galaxy. We will need to have a function for the bulge, a function, and the bar is very difficult because it's elongated, right? But we need, so the bar is going to disturb the functions that we'll try to model to fit the bulge information and the disk information. This is what brings complexity for the modeling.
Thank you, Yara.
Okay, thank you, Rahul, for the question. Any other question, comment? If not, we can close our seminar. And thank you very much, Yara, for the insightful and engaging presentation. I truly appreciate I truly appreciate you for taking time to share your presentation and experience with us. And we hope to have you in the future to share more about the upcoming results that you'll have. And thank you everyone for joining. See you next week. Have a wonderful day.
Thank you. Goodbye.
Bye.
Thanks. Cheers.
Thank you, Yara. Bye.